Hello, and welcome virtually to Brookhaven National Laboratory. I'm Bob Gordon, and I manage the U.S. Department of Energy's office here at BNL. Before you begin exploring this amazing place, let me tell you about the Department of Energy, Brookhaven's owner. The Department of Energy's Office of Science provides most of the lab's $700 million annual budget. We've hired Brookhaven Science Associates, a partnership between Stony Brook University and Battelle Memorial Institute, to run our laboratory, and especially the conduct of world-class science. You probably didn't know that the Office of Science is a world-leading supporter of research in the fundamental sciences. Battelle and Stony Brook are both leaders in science, education, and research. Together, we strive to realize the DOE mission to ensure security and prosperity through transformative science and technology solutions. And you're part of it. Welcome to BNL's Summer Sundays and enjoy the visit.
Hi, welcome to the U.S. Department of Energy's Brookhaven National Laboratory. Thanks for joining us virtually as we share our groundbreaking research and unique facilities with you online. Today you'll get a video tour of the Center for Functional Nanomaterials, or the CFN, one of 5 nanoscale science research centers funded by the Department of Energy's Office of Science. Here, scientists use specialized tools and their expertise to explore the fascinating properties of materials and processes at the nanoscale. We look forward to seeing you in person in the future, but for now, your tour guide is inside and ready to show you around. Enjoy!
Thank you, Kahil, and thank you all so much for joining us here today. My name is Aaron Stein, and I'm a staff scientist here at the Center for Functional Nanomaterials, or the CFN. Here at the CFN, we're studying materials on the nanoscale. The nanoscale is a size scale from 100 down to 1 nanometer. A nanometer is 1/1000th of a meter, so very, very, very small. This is the size scale where light interacts with matter. It's the size scale of the chips inside your computer or the phone in your pocket. It's the size scale of many biological functions. It's also the size scale of the COVID-19 virus, which is about 100 nanometers. We're studying all of these kinds of materials and more here at the CFN. And today I'm going to take you around for 5 different stops and talk about the kinds of science we're doing. So come on, let's go. One of the important ways we study nanomaterials at the CFN is with X-rays. X-rays are good for looking at nanomaterials because they look at things on a very, very small size scales, and they don't destroy the material they're looking at, which helps us to get information that we wouldn't be able to get through other means. Luckily for us, we're located right across the street from one of the brightest sources of X-rays in the world, the NSLS-2, or the National Synchrotron Light Source 2. So we have experiments that run over at the NSLS-2, and we also have X-ray experiments that run here in the CFN building. One example of this is this machine behind me, which is a SAX machine, which is a small angle X-ray scattering machine. This machine looks at the way X-rays scatter or interact with the material they're looking at and give us some information about how that material is arranged and also the shape and sizes. The nice thing about it is that it's non-destructive, so we can look at materials that we wouldn't be able to look at through other means. At the CFN, we're experts in self-assembly. One way our scientists use self-assembly is through DNA. Yep, the same DNA that you learn about in biology, we can use as a nanomaterial to guide the formation of structures of nanoparticles. Another form of self-assembly is by using polymers, or a special kind of plastic, to form structures that would be almost impossible to form through other means. We can use the SAX to look at how these materials are structured and understand how they're formed, and also what applications we might be able to use them in. Next, we'll be looking at another way we use X-rays to study materials at the nanoscale. One of the main things we want to do at the CFN is look at and characterize materials on the nanoscale, which is very challenging because these materials are very small. It means we can't look at them with conventional microscopes you might know from your school. So we have specialized microscopes like this one behind me to look at materials at a very, very small size scale, actually down to the atomic size scale. These microscopes are called transmission electron microscopes, and they use very high energy beams of electrons to look at materials at the nanoscale. At the CFN, we have 5 TEMs. Each of them has different characteristics for looking at different kinds of materials in different kinds of environments. This microscope is special because this allows us to look at materials in operando, which means we can look at the materials while they're working. This is important because while we can always look at materials on a very, very small scale and understand the structure of these materials, it's also important to know how that structure relates to its function. For example, in a battery, we can look at materials in a battery under very, very high resolution all the way down to the atomic scale. But it's even more important to look at these materials while they're doing the thing that a battery does, for example, charging up or discharging. This allows us to see why some batteries might fail after a certain amount of time, as we all know from our phones. There are many, many applications we can look at with this in operando microscope, and so users will come to the CFN with their problems, and we can help solve them all the way down to the atomic scale. And for our next stop, we're going to look at a different kind of microscope. Another type of microscope we use to study materials at the nanoscale is a scanning probe microscope, like this one behind me. This is actually a microscope. This is a low temperature scanning tunneling atomic force microscope, and it uses a very sharp tip to probe the surface of materials. This is a custom-built microscope. It works at very low temperatures. This microscope allows us to look at materials in ways that we can't do any other way. Scanning this probe, we can image individual molecules and see the way different atoms are incorporated into these molecules, which is useful for a lot of different applications. One example, a user from Exxon is looking at petroleum in ways they can't look in any other way. So when we have petroleum that comes out of the ground, there's a lot of pollutants in there, and it is refined to try to get as many of them out so they don't go into the atmosphere. But it's impossible to get all of them out, and so there are molecules like sulfur and nitrogen. When that gasoline is burned, it goes into the atmosphere and causes pollution. This microscope allowed Exxon to go through and look at individual molecules and see how those sulfur and nitrogen were bonded into the petroleum molecules, and will point them towards ways of better refinement to reduce the pollution that goes into the atmosphere when those fuels are burned. This is one of many applications that can be used with this custom-built microscope here at the CFN. Next, we're going to go look at a way that X-rays can be used to study nanomaterials in different ways. Another way we use X-rays to study materials at the nanoscale is with a machine like this, which is an XPS, which stands for X-ray photoelectron spectroscopy. This machine is specialized to look at surfaces. Surfaces are very important in chemistry because that is where the action happens, surfaces and interfaces. It's where atoms of one material meet atoms from another material, and so that's usually where there's some sort of interaction that we're interested in studying. One example of this is catalysis. Catalysts are important for a whole range of applications, particularly in energy applications. For example, fuel cells in the next generation of automobiles. The reaction in a catalyst happens on the surface, and so we're very interested in studying the chemistry of that surface and how it relates to how the catalyst functions. Of course, we can look at this under very, very high vacuum, so the vacuum of outer space, but this doesn't help us to see how that catalyst might work in the real world. So we have a special XPS, an ambient pressure XPS, which operates at pressures closer to what we find in the environment that we live in day to day. And this allows us to look at catalysts and the chemistry of their surface in a more real world environment. Next, we're going to go to the CFN clean room, where we can make things all the way down to the nanoscale. So far, we've seen many ways that we can use microscopes and specialized instruments to look at things on the nanoscale. One of the other things we do at the CFN is make things on the nanoscale. I mentioned earlier self-assembly, which is a way of materials assembling on their own, something called bottom-up fabrication. But many times we want to make things more custom, and we're going to use top-down fabrication or lithography to do that. We can draw designs using electrons, ions, ultraviolet light, or lasers to make patterns from down to tens of nanometers up to many, many microns, so scanning many different size scales for different applications. Then we can turn those drawings into different materials of all sorts depending on the application. CFN users use the Nanofabrication facility over a wide range of applications. People are interested in looking at the next generation of materials that might go into your computers, including quantum computers. People are interested in making structures that copy what they see in nature to try to capture some of those amazing things that Mother Nature's come up with on its own. People are interested in looking at materials that might go into your solar cells or displays. Pretty much anything that our researchers can think of, we can help them make inside the CFN nanofabrication facility. Thank you so much for joining us today. I hope you've enjoyed our tour of the Center for Functional Nanomaterials. Now back to you, Kahil.
Thanks, Aaron, and hello again. Now that you've seen what's inside, you might have some questions. So we've gathered a group of scientists that work at the CFN, and we'll be streaming them starting now. This is a live online discussion, so be sure to join in and ask your questions. Enjoy!
Well, thanks, Kahil, and hello there, everybody. My name is Abram Ledbetter, and I'm the chair of the CFN's User Executive Committee. I'll be today's host for the CFN Monday. I hope you all enjoyed that video. Let's do a quick definitions. So what's the CFN? The Center for Functional Nanomaterials. And what are nanomaterials? They're materials so small or that have physical features that are so small that their dimensions range in size from several nanometers to hundreds of nanometers. That would be larger than an individual atom, perhaps a large cluster of atoms, but smaller than the width of a human hair, which is approximately 100,000 nanometers. It turns out that in this size range, some materials exhibit size-dependent optical, electronic, mechanical, and chemical properties that don't appear at much larger physical dimensions. And in some cases, those properties may have useful applications, and therefore we call them materials. So, the Center for Functional Nanomaterials, or the CFN, is an awesome facility with awesome people. And it's loaded with tools that can make and or investigate these functional nanomaterials. Some of the tools are so unique and special that they exist only in a few facilities around the country. So people come from far and wide to use these tools, and we call them CFN users. So the CFN User Executive Committee, which I'm the chair of, is a small group that represents the full body of users to make sure that our facilities meet their needs and to make sure that they have a great time while they're here. So, now that we've had an introduction to the CFN, let me introduce you to some of my friends here at the CFN. Starting with Ashley Head. She is the chemist in the Interface Science Catalysis Group. Suyan Wang. She is the material scientist in the Electron Microscopy Group. Aaron Stein, who is the physicist in the Electronic Nanomaterials Group. And Christine Wang, a material scientist in the Soft and the Nanomaterials Group. All right. So I'd like to read a couple of statements, and I'm going to allow you guys to tell me which of these is true or false. I want the audience to kind of think about it and be curious about which of these might be true or false. So, Ashley, is it true that you lived in Sweden for 2 years, or that you drive a motorcycle most days? Give us a little introduction, Ashley.
Yeah, thanks, Abram. So, my name's Ashley Head. I'm a staff scientist here at the CFN, and I use X-rays to watch chemical reactions on surfaces. And I help users, so these would be other scientists from all over the country and all over the world. They'll come and do an experiment with me, and I help them use the special equipment that we have here at the CFN. And I wish I drove a motorcycle to work every day, but I've never driven one. So I have lived in Sweden for 2 years. So as a scientist, there's lots of opportunities to travel. And I grew up in West Virginia. I got my PhD at the University of Arizona. I lived in Sweden for 2 years. I lived in California for 2 years. And then I landed here in Long Island. So I use the opportunity to travel when I can.
Thank you, Ashley. All right, Soo-Yoon Hwang. Let's see. Is it true that you enjoyed paragliding in Switzerland or that you saw the Northern Lights in Canada?
Hi, I'm Suyan, and I'm a material scientist in CFN. I'm using electron microscopes to reveal the atomic structures of nanomaterials. During the work, I'm focusing at very tiny nanowork. So when I'm not working, I like to explore much bigger things instead. For example, I enjoyed time in Switzerland to see the huge Alps mountains and feel the mountains through the snow sledding and paragliding. So my true statement is I enjoyed paragliding in Switzerland. The next thing I really want to do is seeing Northern Lights somewhere. Aurora borealis is the result from the interaction between the charged particles from the sun, like electrons and protons, and Earth's atmosphere. Considering electron microscopes are using the interaction between the sample and electrons to study the material's property, the polar lights are a much bigger version of electron interaction, which fascinates me. So also they are very pretty from the picture. So one day I want to explore aurora someday.
Well, Soo-Yan, that's amazing. And I can tell you that if I had a choice, I would prefer paragliding than I would lights. But, anyway, both of those are very cool. Thank you so much.
Thank you.
So, all of these true-false statements come from my friends here. So I'm curious to know which of these are true or false either. I thought I saw Ashley riding a motorcycle one day. I'm just joking. All right, so now, fine. So which of these is true? That you met your wife in the 3rd grade, or that you play the tambourine in a small funk band called the Nanometers in your free time? Aaron, go ahead with your...
Hi, Abram and everyone. My name is Aaron Stein. I work in the Nanofabrication facility at the Center for Functional Nanomaterials, amongst wearing many other hats there. I am a staff scientist in the fabrication facility. I've been working at the CFN for 18 years, actually as long as it's been around. And so I guess that's something that I do because I've also known my wife for a very, very long time, since I was in the 3rd grade. And as much as I wish I had the rhythm to play tambourine, I just will enjoy the music and not try to play any. So that's a little bit about me.
Okay, that's cool. I can see you playing the tambourine too, though. All right, Christine Wang. So which of these is that Christine can write with both hands, or did Christine do a 100-mile bike ride? Christine.
Hey, I'm Christine. I'm a research associate at the Center for Functional Nanomaterials. What I do is I design and use DNA nanostructures to use it for biomedical applications, including fighting cancer. So outside of work, I like to do a lot of sports. I do surfing, I do bike rides, I do badminton, and jog a lot. But 4 years ago, I'd like to share that 4 years ago, I started to do road biking. So since I moved to New York from California, and before that was in UK, I pick up road biking, and every year I would train, and then I would go to New Jersey to do this called Twin Lights ride. So the first year I did 55 miles, and the second year I decided to challenge myself to do 100 miles. And last year I did 75 miles. So if this year, if it's not the virus, I would have done 100 mile again. So very excited about next year.
That's incredible. That's really incredible, Christine.
Thank you.
To our audience, we're going to now do a true-false set of questions for my panelists. And while we're asking these questions, I want you to think of some questions that you might want to ask of our panelists. And you can do that by typing them into the chat. In the meantime, when these questions are read, feel free to type into your chat box either true or false. And our panelists are going to answer these questions to indicate which is true or false. So number one, CFN science is about the size of the width of a single human hair. Ashley.
Yeah. So you mentioned in the introduction how wide a human hair is. And nanoscience is actually looking at things much, much smaller than the width of a human hair. So you would actually have to take a human hair and slice it 10,000 times. And then that one single piece would be on the order of a nanometer. So in fact, your statement is false. We do things much, much smaller than the size of a human hair. And the reason the nanoscale is so exciting is because elements have different properties the smaller that you get. For example, I have some props. So a pencil, it has carbon, known as graphite, and it's really soft. So you can write on a piece of paper, right? Because you're putting carbon on your paper, it's so soft. But do you know what element is in diamond? That is also carbon. So diamonds are really, really hard. They're seemingly the opposite of this pencil, right? Which is so soft. And then if you go in between that, carbon as a nanomaterial, okay, if you put a piece of Scotch tape around your pencil, you can get off a single layer of carbon atoms on this piece of Scotch tape. This is called graphene, and it has these really special properties that is so strong. But there's a little bit of a problem with it, right? It's a tiny speck. You can't even see it on my piece of Scotch tape. So at the CFN, we're doing things, we're studying graphene to see its special properties. How strong is it? But we have this problem that we need bigger pieces of graphene in order to make use of these special properties. So that's one reason we study things on the tiny scale. We need really special tools. So that's why you need a whole big building and a whole facility for scientists all around the states and all around the US to come and use our equipment. For example, I have here too some teeny tiny heaters. So these are chips, and they have some printing on them that you probably can't see because they're so shiny. And they're heaters that are actually about the size of a human hair. And then we can we can put nanomaterials on these chips, and we can look at them with electrons like Su-Young does. Or we can look at them with electrons, like I do, and we can look at the chemical reactions, so I can see what different gases are sticking to the nanomaterials. Su-Young can look and see how the materials are changing over time. So those are some neat things we do here at the CFN, and a little bit about the scale of nano.
Great, thank you, Ashley. So we're interested in looking at things that are really, really, really tiny. But this next question is for Su-Young. And again, true or false? Feel free for the audience to put this into your chat box, true or false. The CFN has microscopes that are as big as a person. Is that true or false?
The CFN has lots of different kinds of microscopes. Some are the optical microscopes you may see in science lab, which are small, but the others are quite large, as big as a person, or they are even bigger than me. So this is true statement. So big microscopes are electron microscopes, which uses electron to illuminate the sample. To see tiny details of samples, electron microscopes need a lot of lenses to focus electron beam and magnify the results we got. And transmission electron microscope usually have 3 types of electromagnetic lenses, and thanks to the complex optics, we can resolve even atoms. So we need very big microscope to see very tiny things.
Excellent. Thank you, Suyan. Third question. This is for Aaron. Nanomaterials can only be made by scientists building and putting them together piece by piece. Is that a true or false statement?
Well, that is one way that we make nanomaterials or nanostructures. We can do them from the top down, meaning we can come in and move things around piece by piece or draw things using electrons again or ultraviolet light. This is how all the chips in your computer are made all the way down to the nanoscale. So that is one way we make nanomaterials, is sort of piece by piece, just like you might make something in arts and crafts, but with very expensive pencils and pens. But another way is materials that put themselves together on their own. We call that self-assembly. And there are actually many examples of self-assembly in nature. Mother Nature puts together materials all by itself. It doesn't need us to do it. And we see plenty of beautiful patterns of things that have been assembled just because that's the way the materials want to do it. And so scientists at the CFN can take advantage of things that Mother Nature or the materials or the chemistry wants to do on its own to create structures that might be useful for us. So we want to understand why the materials try to form the way they do, and then we want to be able to take advantage of that to create structures on our own. And sometimes that makes things either easier to do than we would be able to do otherwise, or it creates structures that maybe would be impossible to make without using what we call this bottom-up fabrication or self-assembly. So we, at the CFN, as I mentioned in the video, we use polymers to do self-assembly, a special kind of assembly called block copolymer self-assembly, where these materials like to align themselves in shapes like dots or lines. And we also do self-assembly with DNA, which is something that Christine is an expert in for doing things. So DNA is a nanomaterial that we can take advantage of because we know it comes together on its own. We don't have to tell DNA how to assemble. So the answer is false. We don't have to do all of the fabrication on our own. We can take advantage of what the chemistry or materials want to do on their own.
Great. Thank you, Aaron. One more true-false statement, and then I'm going to go to the audience because we have some interesting questions from our audience. And this true-false statement is going to go to Christine. DNA origami is when scientists fold DNA into shapes like in paper origami. True or false?
This is a true statement. So as Aaron is saying, DNA just likes to go together. So we use this property, basically design DNA origamis, where we can glue together pieces of DNA and make them into 2D and 3D shapes. So something like cubes, spheres, bricks, and other kinds of geometrical shapes can be easily designed using DNA. So it is like folding a paper origami, except it is so much smaller. So as we talked about earlier, we're looking at in the nanometer level instead of centimeter that we can fold a paper in our hands. So the reason that DNA can be programmed into these desired shapes is because they have these complementary base pairs and they can easily just self-assemble and bind together to form these double helix and twisted ladders and more complicated structure. So by using these DNA glue and origami structures, the scientists here at CFN, they can use these structures and DNA glues to instruct other types of materials like nanoparticles, and then they can also form them into 2D and 3D shapes.
Wonderful. Thank you so much, Christine. All right, now for the first question, and I'm going to open this up to our panelists. Each of you that wants to can answer this. This comes from Donna on Facebook. She wants to know, what is your favorite material created via nanofabrication at BNL?
I guess I can take that. I do work a lot in the nanofabrication facility. So what is my favorite material that's been made in the nanofabrication facility? Well, that's a good question. To think about favorites, it's hard to play favorites. So as Abram mentioned at the beginning, one of the things we do is work with a lot of users. So we have scientists coming from all over, and they have a lot of really interesting problems, and we get to help them solve them using our expertise. And so that's a lot of fun. So I don't want to play favorites from anyone. Not that all my users are watching right now, but one of the projects that I've always really enjoyed working on with some collaborators in Europe who are interested in looking at magnets and looking at magnets when they get very, very, very small and they can be put together in really interesting arrays. And we know magnets, of course, magnets have a north pole and a south pole, and north don't like to stay together, and north and south do like to stick together. And when you make these very small and very large arrays of very, very small magnets, and you have the physics of what happens is very interesting, because you can't always have north facing south and south facing north. At some point you can't have that, and then you get to start having a lot of interesting physics, and that can be used as a model, because a magnet is a two-state material. It's got a north and a south, and we know charged particles have a plus and a minus, and we know in gravity we have things there's a lot of two-state systems in the universe, and so we can use these magnets as a model for other systems, and it's really kind of fascinating physics, all just from a very, very simple magnet. So I always enjoy those, and they actually look very beautiful when you make them as well. So that's one of my favorite kind of projects using nanofabrication.
Awesome.
I'll jump in a little bit. So
Sure.
I don't fabricate things, so I'm more studying chemical properties. But I love walking around in the CFN, and we have users who take inspiration from nature, because nature does a lot of patterning on the nanoscale anyway, like butterfly wings, or I think there's a poster in the hallway about hairs on ants and how they're triangular. And so a lot of the CFN users will take patterns from, I guess the examples I've given, animals or sometimes even plants, and try to recreate what nature has already done. And those are my favorite things to see what people are always doing here.
And that's an entire area of research that's called biomimetics, where some actually try to mimic nature. And there are a lot of nanoscale features in nature that exhibit incredible properties. And so there are scientists and engineers that are working on ways to duplicate that. So thank you. All right, so our next question comes from a viewer on YouTube. And that question is, was the custom-built low-temperature STM AFM tool custom-built by BNL or custom-built by a third party? Great question, user. Good viewer.
Future user, hopefully, right? Future CFN user.
So I think I could answer that. It was built before I came here, but I'm pretty sure large parts of it were built and custom designed by one of my colleagues, Percy Zoll. So he took some things you have to buy commercially, and then he adapted it to make it have all the great capabilities that it does. And that's something at the CFN, there's lots of knowledge, not only in studying the chemical systems, but we do a lot of either building of equipment or modifying equipment and tools in order to study things on the nanoscale.
Yeah, and there's a lot in technique development too. So, the reason why users come to the CFN, there's a lot of reasons why they come. And one is we've got all these big, expensive machines that we are experts in running, but sometimes they have problems that can't be solved anywhere else. And we have sort of the freedom for users to kind of come and say, look, there's a need for this. There's nowhere else we could do this. And take that and understand what the needs are in the scientific community and try to address them either through buying things or hiring people, or in this case, making something or upgrading something. So there's a lot of it's a very dynamic environment in our center to do those kinds of things. It's actually a very exciting place to work because there's sort of this freedom and this dynamism that you don't maybe not find somewhere else.
Awesome. Thank you, Aaron. All right, so the question is from Curtis on Facebook. He asks, has the CFN looked at UVC for disinfecting a surface? That's interesting, especially in this time where we are curious about ways to combat the coronavirus, and we know that viruses and bacteria are nanoparticles. So anybody want to answer that question?
I think I can say a little bit of that. So I think like in CFN we have been performing all these safety procedures to protect ourselves and also like not to contaminate our samples. So because they were very, very sensitive. In my lab, we have to work all the chemical reactions inside the hood. We have to clean up all the pipette tips in special containers, and we have to wipe it constantly. And there will be safety managers that come to check once in a while, and they will make sure that we have all the safety in line, that so then we can work safely inside the lab.
Awesome. Anybody else want to answer? Or I don't think that there's been any research studies involving UV light, but there are studies that have been done, and so that outside of the CFN, so that could be something for further exploration that you could look into.
I know Ashley's been looking at ways of cleaning PPE. I don't know; it's not quite answering the question, but I don't know. Yeah. That's something you could mention, Ash.
Yeah, so there are a couple different other efforts, I guess, related to the current pandemic situation. So I've been helping some users look at how to clean the N95 masks. So these are in short supply, and so people want to clean them and reuse them. And so we want to make sure that after you clean them, they still offer the same amount of protection as the chemical structure on the surface change, so that they're no longer going to trap the particles. And so we use X-rays to look and see what elements are on the surface of the fibers of the masks. And then the scientists that I work with would go and clean them. These were unused. They were just new masks, and they would clean them with peroxide or put them in a steamy bath or just heat them in air. And then we would look and see, did the elements and the chemical functional groups on the surface change, and can they still trap the virus particles the way that they were designed to do?
Thank you, Ashley. So let's go back to our true-false statements. I'm going to throw this one to Christine. True or false? DNA origami could help fight cancer.
That is a true statement. So the scientists in CFN and collaborate with a lot of collaborators across the United States are studying how these DNA origamis can be made into cages. So then we can load different sizes of drugs, like anti-cancer drugs, into these open space structures. So the DNA origamis, we can make it into different sizes and different shapes, like cubes and spheres and everything. So we can interact with cells differently depending on how the cells were shaped like and how the cells were, their environment looks like. And we can also ask the DNA origamis to carry different sizes and different properties of the drugs. There's, however, a property of DNA origami structures that's not good for biomedical applications, is that they tend to break apart inside the biological fluids, so like blood, because there are so many enzymes in there. So the DNA nanostructures, they cannot maintain their structure and they will break apart. But we need them to make sure that they were in the same structure, so then we can deliver to the disease cells. So what we do in CFN is that the scientists will use synthetic method to design chemicals, like small molecules, that can coat the surface of the DNA origami structures, so then they can maintain their shape and carry these drugs until they reach the disease cells and do their job. So that is very exciting. And this is a true statement that definitely DNA origami has a future of help fighting cancer.
Wow, so many practical applications of nanoscience, right? All right, Suyan, true-false statement. Scientists run experiments at the CFN to study why batteries need to be charged so often. True or false?
Oh, I'm so happy to answer. This is true statement. The scientists and users at CFN look at how batteries work inside. So using electrons and X-rays, we can see how the atomic arrangement and chemical compositions of materials change as battery cycles and as cycles. For example, I looked at the cathode materials for Tesla electric vehicle and saw nanostructure has changed at harsh charge conditions. So linking these nanoscale changes to real battery performance provides important clues how we design new materials for batteries that last longer and charge more quickly.
Awesome. Thank you, Suyan. Next true-false statement is going to Ashley. Scientists have to wait until a chemical reaction is finished to know what changed. True or false?
Yeah, so you often want to know what happens during your chemical reaction while it's going on, because if you just wait until the end, you might miss something. So that's actually false. We use special equipment at the CFN to monitor reactions while they happen. And I can tell you a little story of an example. So here I have a powdered catalyst. So this has molybdenum and nickel on titanium dioxide. And this is used, it's a nice kind of seafoam green, I think, in this cute little tube. This is actually used to break apart biofuel, or to make biofuel. So it breaks down bio oil, which is molecules that you get when you break down plant material, because we want to move away from a petroleum-based economy and sources of fuel. So one of my colleagues that I worked with in Sweden, she came to the CFN to do some experiments with this industrial catalyst from a company in Sweden. And she wanted to know, what is the molybdenum doing while it's breaking apart this bio oil in order to generate fuel that we can use. And so I helped her with using X-rays to see what is the molybdenum doing. And we also used infrared light studies to see how the bio oil is sort of sticking to the surface, and then what chemical transformation happens, and then what products come off. So we do lots of things in real time. We even have a little a probe that has a tip that scans a surface while it's under pressures of gases, so we can see where oxygen atoms are landing and where they're reacting with carbon atoms on a surface.
Thank you, Ashley. And viewers, I would encourage you to continue to send us your questions. You can type them into the chat. All right, another true-false statement. And this one's going to go to Aaron. So I don't know. A long time ago, there was this movie called Honey, I Shrunk the Kids. And what happened is that they went through this metamorphosis where they just got shrunk down to extremely tiny sizes. And so, of course, they needed really tiny clothes. So this next true-false statement is, nanofabrication refers to making tiny clothes. True or false?
Well, you know what I say, I work in the nanofabrication facility, and when I like to talk to people about what we do there, and I always say that this is where the magic happens, because we can make whatever anyone dreams of making in any material or any size scale they'd like, from tens of nanometers to tens of microns. And so I suppose if someone came to me and said, I want to make a pair of nano Levi's, I think that me or my colleagues in the nanofabrication facility, we maybe would be able to figure it out. But that's not what nanofabrication is used for generally, or 99.9% of the time. Usually we're making things that are important to study different materials or different structures for all sorts of different applications. And that's so, nanoscience is not just one kind of science. You've already heard about biology and chemistry and materials. And so when you're doing nanofabrication, it's the same kind of thing. Sometimes we're making structures that are interesting because they mimic nature, as we talked about, or are interesting for watching cells grow or move around. But sometimes we're looking at materials that might go into your computer or solar cells. So we're talking about materials. And sometimes, like the thing I talked about with the magnets, we're just learning about physics. So, there's no nano tailors yet, but maybe someday that'll be something to think about. But nanofabrication really deals with making things on a small scale, typically typically not close. So I'll say that's false for now, but who knows? I don't want to sell the field short. Maybe someday.
Well, you know what? So they did functional nanomaterials, so they have some useful application. We never know. There might be this device one day that does actually shrink people down to that nanometer scale. So we never know, but so that could be a functional thing.
And you never, you can always extend it because I just realized that there is nanoscience in clothing too, and we have stain-free pants. Those use nanostructures to repel liquids because, and that's actually sort of a biomimetic thing where we know that certain structures in nature repel liquids, and people have incorporated that into clothing. And there are also people that are trying to come up with things like low-cost materials that could be used for solar cells that, could be sewn into a shirt or something of that nature. So, and we use nanofabrication to study those materials, to structure those materials, to learn about them. And so, I know this was kind of a joking question, but, if you dig deep enough below the surface, things like nanofabrication and nanoscience really are all over. They're in your clothes, they're in your pocket, and so true and false.
Absolutely. Okay, I'm going to return back to the audience question. So let me ask this question. This comes from Peter on Facebook. What is the most unexpected result you have observed on the nanoscale? The most unexpected result.
Who wants to take that?
Takers? Or maybe not. Accidents do happen, and also sometimes in science research, there are findings that are unexpected, and sometimes those are good, and sometimes they're not as pleasant. Has anyone observed either of those scenarios?
Yeah, I could talk about something. So one of my research projects is looking at the absorption of chemical warfare agents on gas masks, but I don't use the real chemical warfare agents. We are not equipped to do that. We use simulants. So something that is not deadly at all, but it sticks to gas mask filters just like a chemical warfare agent would, for example. And so the gas masks is this powdered carbon. So that it kind of looks like stuff in your water filter at home. And this carbon is porous. And inside the pores, there are metal oxides like copper oxide, molybdenum oxide. There's some metallic silver. And I study how these metal oxides trap the chemical warfare agent simulants and decompose them. And one thing we found out is people sort of thought that copper didn't do anything, but it actually traps molecules similar to sarin really well and breaks them down to just pure phosphorus, which is really, really amazing. We didn't know that it would do that. We thought it was mostly just the carbon absorbing the stuff, but actually the metal oxides play a huge role.
Well, that's actually a good result.
Yes. Yeah.
Yeah, good unexpected result. A question from Anna on Facebook. She asks, has the CFN done any projects exploring surface interactions during experiments using plasma catalysis?
So we don't do any kind of plasma catalysis, but in our nanofabrication, we use different plasmas in making different kinds of films. So I know that we can deposit different metal oxides using plasmas and putting in the right metal precursor molecule. Maybe Aaron knows more specifics about the plasma deposition process or cleaning. Plasma is a great way to clean things.
Yep.
Yeah, absolutely. We do use plasmas. We don't. I wouldn't necessarily ascribe it. Use that with catalysts, but certainly for they're very important for yes, cleaning surfaces, etching surfaces. Some deposition is so. There's a lot of plasmas. Plasma is a lot of ions. And so those ions are usually very reactive with surfaces, and so they may eat away at surfaces, and so you can etch things. They may react with surface, so you can grow things, and so those are the kinds of tools we use or etch things of materials that can't be done other ways. So plasmas do play a important role in the CFN, and that's why when you walk through, you see a lot of vacuum chambers. One of the reasons why is we have sometimes plasmas in there or other things, but not with catalysis necessarily at the CFN.
All right. Next question comes from Evan via email. Which area of medical treatments do you think nanotechnology would help most? Thanks, Evan.
I can take this question. I think it will help for nanomaterials for biomedical applications. It's really broad. I cannot say which direction that will help the most. But for a new material, for example, a new nanomaterial, so to make a drug or to make a medical device that goes inside the body, you need to have a lot of approval for the safety and efficacy at the same time. So in order to develop something, new material for biology, a lot of times we will start with something that's biosensing or like diagnosis, that you can take out your samples and measure with the nanomaterials instead of the other way that you put the nanomaterials inside the body, because it takes a lot of time and a lot of effort and a lot of approval for getting these materials that's known property and known size, known surfaces to bring into the body without causing any side effects. So it is very important to know the material's properties before we engage in biology. But there's definitely a lot of futures because of how the cells in the same level as nanomaterials, or how the proteins and DNA and genes are in the same level as nanomaterials. So then we can definitely, if we can prove the efficacy and safety, then we can definitely have a future of using these nanomaterials to engage in biology and make it more therapeutic, effective and more sensitive for diagnosis.
I think generally, there's people studying so many different aspects of medicine using nanomaterials, and so I think it would be hard to say, well, there's one that's going to be more effective. Yeah. But I think Christine talked about sensing is very important. I think you can see it now with our current pandemic, being able to sense small amounts of materials, but therapeutics, all of these things, even with the current COVID-19, we're talking about working with nanomaterials. Imaging, sensing, therapeutics. And so there's so many different ways that it would be, to say which is going to be the most. But I think rest assured it'll probably have a hand in a lot of those areas, probably all of them, right? Some way.
Yeah, I agree.
A question in that same vein. So, and this comes from a viewer by email. How will nanotechnology benefit our healthcare workers and first responders? Are there any near-term uses for PPE and patient care, such as respirators and ventilators? And Ashley, you touched a bit on that. But Ashley or Christine, could you give us your thoughts?
Yeah, so we've looked at cleaning the masks, as I mentioned. So using our tools to study different mask fibers and how different cleaning procedures affects that is a very immediate need. And I know that the collaborators working on that project at other national labs are coming up with new ways to synthesize new, better fibers that are more tailored to trapping the coronavirus and not just any particle of any size. So that's something that's in the works right now, is to make these masks even better, not just through cleaning, but developing even better fiber material.
So in my view is not making materials as Ashley is saying, but because virus is a nanomaterial, basically is in the size of 100 nanometer. So I think it's definitely that we can use our experiences of working with nanomaterials, how we protect ourselves and create a barrier. And these experiences can be transferred to how we protect ourselves from virus, which is also in the same level and also toxic to our human body.
Thank you. So this next question comes from Inkuru on YouTube. So what material acts the weirdest at the nanoscale? Any materials that just seem to have really interesting properties when you get to the nanoscale?
Well, one interesting material is gold, right? So gold is a material that everyone knows gold, and one of the reasons why we all know it is it doesn't react. And you can have a gold ring that's very old, and it's still, you can shine it up and it's a gold ring, and it doesn't really, that's one of the things we like about gold. It's beautiful and it doesn't react. And so, but then when you have nanoparticles of gold, they start doing the exact opposite. They do a lot of, they can be used, they're an example particle for lots of different kind of applications. And so it's almost, it does a 180 when it gets down to the nanoscale. It's a pretty good example of material that's used, in a range of different things, therapeutic catalysts, and so it's weird in a way that it doesn't react the way we think it does. And I think, Ashley pointed to carbon as well. So sometimes it's the simplest materials that once they get to the nanoscale are just exactly the opposite of what you might think. And so that's the interesting thing. That's the fun part, where you're in a completely different realm where everything, black turns white and up is down. And that's really what happens at the nanoscale with a lot of these sometimes very, very common materials.
I can give another example of that. So, speaking of gold, I have what we call a gold single crystal. So that is a big hunk of gold that's nearly atomically flat. And we have not only gold, but we have platinum, ruthenium, palladium. And my colleague, Anibal Baskabowinik, takes silica and grows really thin layers of silica on top of crystals like these. And silica is simply sand, silicon dioxide. So the same two elements that are in sand, he grows them on these these precious metals, okay? And then they change the properties of the precious metals. So they induce a really high local pressure underneath the thin layer. And it can change the catalytic properties. So reactions run at much, much lower temperatures. They run at lower pressures, things like this. And it's just sand, but in a different form. So that's what Aaron's saying is it's really cool about the nanoscale is the same elements you see every day and think about every day. Once they go small, different things happen.
And so it's our job to kind of figure those things out and then work with people to figure out how can we use those things to solve problems that everyone has. So that's really, like, in a nutshell, kind of what we do at the CFN.
So viewers, get ready, because we're going back to the true-false statements. So you can indicate right there in the chat if you think this statement is true or false. So, Aaron, I'm sorry, Ashley.
Yep.
Catalytic converters in cars use precious metals, since you were just referring to those, like platinum, as catalysts in chemical reactions to reduce harmful emissions in exhaust gas. True or false?
Yeah, so cars have, catalytic converters. They're these really big things on the end of your exhaust pipe, right? And they actually do contain precious metals like platinum because they work really well. I think the support that they're on is cerium oxide, and then inside sprinkled is a bunch of platinum. And once they get to a specific temperature, they start reducing the pollution. And this makes catalytic converters really expensive if you ever have to replace yours. And we would like to do something much cheaper. One example is iron. Iron is everywhere. It's a more common metal. It's cheap. It's steel. Lots of things are made of steel. But then iron catalysts can do the same thing as platinum, but they don't last as long. Or maybe there's some side reaction that happens that prevents it from working the decades that your catalytic converter does. So that's one of our jobs, is taking current catalysts that are used and trying to find cheaper alternatives, more abundant alternatives, things like that.
Thank you, Ashley. All right, next true-false statement. This goes to Sue Yan. Companies can't conduct battery research at the CFN. True or false?
The CFN facility is open to the users from both academia and also industry, so this statement is false. For example, we had scientists from Toyota car company, and they did some battery experiments at CFN for many years, and they published nice papers. And we are always welcome users from industry.
Thank you, Suyan. Aaron.
Yeah.
True or false? CFN scientists have made glass so anti-reflective that it's practically invisible. True or false?
That is true. That is true. So that is something that was done by scientists at the CFN using self-assembly technique. And so the nice thing about self-assembly is that you can make small nano patterns over large areas without a lot of problem, because it wants to do it on its own. And so scientists use that technique to make sort of cone-like shapes, and they've done that in silicon. And when you do it in silicon, it makes the silicon very highly anti-reflective. So it's actually sort of a biomimetic structure. It looks like what a moth's eye looks like. And so these little nanostructures allow most of the light that comes into the structure to go in and not to be reflected out. And that's good for solar applications and a lot of other applications. Similar structures made in glass allow the light to go, all the light to go in and very little to be reflected back again. And so no matter, you always look at your glasses or your telephone, and there's always some glare on it. And so even though glass is transparent, it always has some reflection. And so putting these nanostructures using self-assembly on glass creates an invisible glass, where no matter what angle you hold it on, the light goes all the way through. And if you look at this, it almost looks like it's invisible. And I would definitely encourage you to Google that BNL invisible glass, and you can see what I'm talking about.
Thanks, Aaron. And I'm going to field this true-false question to any of you all. And I think the viewers will already know the answer to this one. So, only chemists work at the CFN. True or false?
Totally false.
I mean, because you all are not.
I am not. Yeah, I am not a chemist. I mean, kind of. I synthesize things, but a lot of times I work with materials, how to engineer them. I also work with computer scientists here at CFN. Also collaborate with other people to look at how we can optimize the materials, and I collaborate with biology people, how to put our materials into the biological environment. So there's definitely a lot of collaborative environment going on inside CFN and BNL and the whole other community outside.
I'll tell you, I haven't personally taken a chemistry class since high school, and yet I work with chemicals almost every day. So there are, I work safely with chemicals, I should say, but there's I think a lot of this stuff at a place like the CFN, just to expand on what Christine was saying, is we are learning along the way. And so we're learning about materials and how to work, with these new techniques, new materials. And so we're there's a lot of there is creativity in what we do, and learning along the way. And so it's even though we might have backgrounds in certain areas, that doesn't really force anyone at our department to continue on that path. There's lots of interaction and learning along the way.
Yeah, absolutely. So nanoscale science is interdisciplinary and multidisciplinary, as you all have mentioned. So that makes it a really interesting, the work at CFN quite interesting, because there are different people with different research backgrounds, but working together to solve common problems of common interest. All right, so now I'm going to return to our viewer questions. This one is from Matt on YouTube, and this question will be our last question, and that is, are the laws of quantum mechanics applicable at the nanoscale? And
absolutely. Yes, absolutely. In fact, that's where they start kicking in. That's where that's one of the other things that's, a lot of the things we're talking about are because the quantum effects, which happen when things start, you start looking at things in smaller and smaller pieces. Those really, you don't see them unless you're looking at the nanoscale. So that's a resounding yes, and I'm sure we could all come up with examples of those, a lot of those cool, weird things that you read about in quantum mechanics textbooks or popular literature that we're kinds of things that we're trying to recreate or studying every day.
Thank you, Aaron. Well, that will wrap it up for our CFN Summer Sunday. I want to thank our guests, Su-Yan, Christine, Ashley, and Aaron. Thank you so much, guys. And I want to thank you, the viewer.
Thank you.
So, us here at the CFN, have a happy Sunday.
Come visit us next year.